Yes, so now I'm going to show you the calculation for uh, lab 7 losses in pipe fittings. So in the lab you have uh, counted the time, right? You got the time and the volume. Volume was 10 liter and you got the time in second. So you have to convert this liter to meter cube. Then from this you can calculate the volumetric flow rate Q, which is equals to volume divided by time. Okay, then you will get something with meter cube per second. Yep. Now we need to know the velocity of water. Right, so we have to use this formula. Q equals V times the cross section area. So from there you can calculate the velocity of the smaller pipe, right? Vs equals Q by A. Now you need to know the velocity of the larger pipe, right? So for this you have to use the equation like V small a s. So we write it as equals V large a l. So from there you can calculate the VL, right? So VL is VSAS divided by AL. So area, for area find the diameter. So the diameter of the smaller pipe was 22.5 millimeter and diameter of the larger pipe was 29.5 millimeter. Okay, and now you have to find the loss coefficient K for all those fittings. So the formula is HL equals K times V square by 2 times gravity divided by 2 times gravity. So we have to find this K, this K value. Yep, so now let's use the Bernoulli's equation to find the value of K, right? So for miter, elbow and bending, what we got, like we have the pipe, so we have 0.1 and we have 0.2, right? So this is for miter. 0.1 is the water before entering the fitting and 2 is after exiting the fitting. Similarly for elbow, so this is 1, this is 2, this is for elbow, and another, the last one is bending, right? So this is 1, this is 2. So we have to use Bernoulli's equation. One is for 0.1 and another one is for 0.2. So let's write it like this: P1 divided by rho times gravity plus V1 square divided by 2 times gravity plus the elevation Z1 equals this 0.2, like after exiting the fitting, which is P2 by rho times gravity plus V2 square divided by 2 times gravity plus Z2. Now, after exiting the pipe fittings, we will have two types of loss. One is due to the friction and another one is due to the pipe fittings, right? So this is called modified Bernoulli's equation. So for miter, elbow and bending, you see our pipe diameter was same. That means our velocity should be same. So we can write V1 equals V2, and this elevation is very small, so we can neglect it. So we can say that Z1 equivalent to Z2, and this experiment is about minor pipe fittings, minor loss and this minor loss is because of the pipe fittings. So we are ignoring the major loss, which is HF. We ignored it, right? So now we can write P1 equals P2 by rho times gravity plus HL. So HL, the loss, head loss for miter, elbow and bending, the minor loss is P1 divided by rho times gravity minus P2. So this one is H1 and this one is H2. So we can write H1 minus H2. So this H1 H2 is actually the difference. You got it from the manometer reading, right? So this was for 1 and this was for 2. So you have to take the difference between these two in millimeter. So that is the head loss for miter, elbow and bending. So from there you can easily find this one, right? So we have 5 different velocity. So V 5 velocity reading. So for each 5 velocity reading you get 5 HL, right? So plot it. So HL equals K times V square by 2 times gravity. So consider these as y-axis and this whole thing as x-axis. So it will be like y equals mx type equation, right? So it should be a linear relationship. So your x-axis is v square divided by 2 times gravity, y is HL. So you have 5 different velocity reading, right? So plot it in Excel. Right, you have 5 different readings and draw a linear trend line. And from the linear trend line, take the slope. So the slope will be equal to K. So that's the thing you will need to find, the loss coefficient K for miter, elbow and bending. Suppose you should have 3 different readings, right? Each of the fittings will give different slope. So you have to find K. And this is true only for, as I said, miter, elbow and bending, because their pipe diameter is same. But when you are considering the expansion and contraction, you cannot just cancel out this one, because the velocity is not same for expansion and contraction, because the pipe for expansion is larger and for contraction we are entering a smaller pipe. So there are 2 different pipe diameters. For V1 is V1 and V2 is not equal. Okay, so for expansion and contraction, for expansion, right, yeah, for expansion our pipe was like so this was the smaller pipe and suddenly the pipe diameter increased, right? So the pipe flow direction was into this direction. So we have a smaller pipe and the larger pipe. So here we can say velocity at a smaller pipe and velocity as larger pipe, VL, right? So this, at this smaller pipe the velocity should be higher than the larger pipe. So VL is less than Vs. So from Bernoulli's principle, what we know, like if you have a low velocity, that means you have a higher pressure there. So we can say that PL is greater than PS. Yeah. So in the Bernoulli's formula, so let's write it again. So this is 1 and this is 2, right? So let's write it again. PS divided by rho times gravity plus Vs squared divided by 2 times gravity plus Zs equals PL by rho times gravity VL squared plus ZL plus HL. So this is cancelled. So we can write HL equals PS divided by rho times gravity minus PL plus Vs square by 2 times gravity minus VL square. Okay, so this one is again H1 and this one is again H2. Yeah. So this H1 and H2 again you will get it from the reading. So this is 1, this is 2. So for expansion you should see a negative value, because you see, as I said, this PL is larger than PS, that's why you got negative value. So PL was higher, the part 2 after exit the height was higher than the uh, inlet, right? So this should be negative delta H plus, don't put negative because you already have negative value here. Yeah. So Vs is the velocity in the smaller pipe and velocity in the larger pipe. So this is for expansion. And for contraction, so we have a larger pipe, and suddenly the pipe diameter decreased, right? So we have velocity in the larger pipe and we have velocity in the smaller pipe. So here in the smaller pipe the velocity should be higher, right? So Vs is greater than Vl and the pressure will be opposite, right? So Ps is less than Pl according to Bernoulli's principle. So this is 1 and this is 2. So we can write P L divided by rho times gravity VL square plus ZL equals PS. So we are ignoring the friction loss. So these two cancelled out. So we can write HL equals PL minus PS and plus VL square.
Joel, should I just say submit?
Yes. Again, so this one is H1, this one is H2. So delta H plus VL square minus V square by 2. Yep, so this H1, H2 again you will get it from the calculation, from the piezo, the manometer, right? And take the difference, 1 and 2. Yep, so now you will plot again. You will plot, here you use the smaller pipe only, Vs square by 2G and HL. Now you have 5 readings, so plot one for contraction and another one for extension and get the slope, and the slope will be like, it's the same formula, right? HL equals K times Vs square by 2G. So you have the slope will be equal to the loss coefficient. So finally you have to compare the K values. The feeding which has the lowest K value, that means this is giving you the least loss, and the highest one is giving you the highest loss. Okay, so yeah, you have to plot two different figures, one for miter bending elbow and another one is for expansion and contraction.